We had previously discussed geometric series, and that was actually a form of a power series. A power series is of the form, but just wanted to introduce a power series within the sort of the context of different types of series, because we've been talking generally about series lately. Today we're going to get into specifically power series, and the reason we're going to talk about power series is because Taylor series is where we're building up to, and Taylor series is a power series. So we want to introduce power, and then we'll move on from this into Taylor series. But just to give you a little bit of a context, a different type of series might be a trigonometric series. A very famous example of that is the Fourier series, which is of the form of with trigonometric functions here. Instead of up here, it's called a power series because we just have our x term to a certain power. Hence the name. Trigonometric series would just include trig functions. So let's introduce power series. So up to now with series, we've been talking about sequences that have advanced with n. We haven't really been talking about functions with x, but now with power series, we're going to sort of combine functions with continuous x values to series with discrete n values. And that's what's kind of going to be a little bit more complicated about where we're heading with power series. So we have our function f of x, which is going to be a series where n is increasing from 0 to infinity discretely, but our x is our variable that will change continuously. This c sub n term is going to be our coefficient. And our coefficient typically is going to be a value that changes as n changes. And as n goes from 0 to infinity, it'll change with n. And another thing we're introducing here is a, which is our center. Important to remember this definition because oftentimes you'll be asked to find the center, and it's just simply a. And finally, as mentioned, we have x, which is our variable, which can vary continuously. So if we were to write out the first several terms in this series, we could start off with n equals 0. And so we just plug in 0 up here for n. Term here would just go to 0, so it would be 1. So our first term would just be c sub 0 because we just plug in n equals 0 to find that c sub n coefficient. For n equals 1, we would have our c sub 1 coefficient here, and then we're going to multiply this x minus a. It's going to be to the 1 power. For n equals 2, similarly, we're going to have our c sub 2 coefficient, and x minus a is going to be raised to this second power, and so on for n equals 3, etc. So this is the general form of our power series, and I'd like to introduce this with a very simple type of power series. So let's define some very simple coefficient center to sort of illustrate this. So let's just say our c sub n value is just going to be 1. It's pretty simple, right? Let's say our a is going to be 0, so it's about as simple as we can get so far. And our x is just going to be our variable still. So if we define c sub n and a like that, our power series is just going to be the series of x to the n. Now this may look a little bit familiar to you. If you haven't noticed yet, this is actually a geometric series example where this x is sort of taking that place of our what used to be our r term. But now you can think about it as sort of a variable r. So let me pull Desmos in here and we can actually plot this out. So let's just write this summation term in here. We have f of x is equal to the sum from n equals 0. Rather than infinity, just so Desmos can calculate this, let's just go up to say 50 of x to the n. So you can see here that Desmos is actually graphing this out. So I'm getting different values within this range for my f of x. Now, if this doesn't immediately make sense to you, let me try and compare this to sort of a geometric series example. So let's say for a geometric series, in this case our a is just 1, right? Because we don't have any coefficient in front of the x to the n. And let's just pick a point here and say our r value is equal to 0.5. And now I'm going to plot a point here. I'm going to plot r for my x value. And for my y value, I'm going to plot the sum of the series where we just have r to the n. And that's just going to be a over 1 minus r. So you can see it actually plotted this point here, and this point is 0.5 and 2, and it's actually on this black line as you might expect, because this is pretty much what's getting plotted out here. This is plotting out the sum of our series for various r values. So when our r value is 0.5, the sum of our series is 2. If our r value is 0, the sum of our series is 1, etc. So you can see how this is taking a summation, in this particular case up to 50 values, to find each one of these terms for a given x value. So let's define a couple terms here. We're going to define the radius of convergence, we'll define the center, and we'll define our interval of convergence. But starting off with the center, we were already given the center over here, a equals 0, and you can see that is sort of the center of our interval of convergence between -1 and 1 here. So our center is just going to be 0. Our radius of convergence is just going to be the distance of convergence on either side of 0 to this edge of convergence. So this is our r here. In this case, our r is just going to be 1. So our interval of convergence, we're actually going to go from -1 to 1, as you can see here. However, we're not really sure what happens exactly at -1 or 1 typically, and we actually have to test those out. So for a geometric series, we know this is a geometric series. We know that it's only converges for absolute value of r is less than 1. So we know that this -1 and the 1 aren't actually included in the interval of convergence, because we have this less than sign. It's not less than or equal to. Let's go ahead and prove that just to be clear on our steps here. So this is our series up here, and in order to see what happens when x equals -1 right here, we're going to go ahead and find that limit of this sequence as n approaches infinity. So first we're going to look at our left endpoint where x equals -1. We just plug in x equals -1 for this x up here, and we take the limit of that sequence. The limit of -1 to the n is just going to be plus or minus 1, which is not equal to 0. So we can say, therefore, our series at x equals -1 diverges by the test for divergence. Similarly, we can look at the right endpoint where we get from up here where x equals 1, and we find that limit. It's 1 to the n, which is equal to 1 as n goes to infinity, which is not equal to 0. Therefore, we can conclude the same thing. So we can maybe we just put a plus or minus 1 in there. So we know that for either one of these cases, it's going to diverge by the test for divergence. And because we know that this -1 and 1 are not included in our interval of convergence, we can go ahead and put a parentheses here and a parentheses here, as opposed to a bracket, for example, if either of those points were included in that interval of convergence. So this kind of introduces power series for a very simple example of a geometric series. These can get a bit more complicated, and so in the next video, I'll do a significantly more complicated power series, and the problem will be to find its interval of convergence.